Okay, thank you. So, flash pages come to the world when they're full of zeros, and when we want to write on them, we have to program some of those zeros into ones to hold that information that we want. When we want to write again, we can't, because we have to first erase the block that the page belongs to, and then we can start over the cycle again. With WOM codes, we can perform additional writes, which means we turn some of those leftover zeros back into ones, and then we have additional information that's encoded on the page. Again, after this is done, we have to erase the block that the page belongs to, and the cycle begins again. So in Reusable SSD, we perform these additional writes before every erasure, which means we can reduce the number of erasures that we perform, and this extends the lifetime of the SSD. This also improves performance, and we're able to do that while preserving both the capacity and the interface of the original SSD. So WOM stands for Write Once Memory, which is a media where zeros can be turned into ones, but not vice versa. And punch cards were actually the motivation for the first WOM codes that were suggested in 1982. So the idea is to write n bits of information on m cells where n is larger than m. So what we do is you have to take the data, you have to add some redundancy, and you encode it in a different manner for the first write or for the second write. So let's look at an example. Let's say you want to write two messages, 1, 1, and then 0, 1. Normally you would need 4 cells for that. You would have to encode the 1, 1 at the beginning, and then you encode the 0 and the 1 because you cannot overwrite. With WOM codes, you can do that with only 3 cells, because you use the first column here for the first write to encode the first message, and then you use the encoding on the second column to write your second message, and you only turned 1, 0 into 1, which is okay. So within every program and erase cycle, Flash is actually a write once memory, and this motivated several suggestions for using WOM codes on Flash. They're different in various characteristics, but they all have the very basic design in common, which is the user writes the logical data page, and the data is encoded into a larger physical page that's then written onto the flash. Because again, you always have to add some redundancy. So this is done until the block is full, first with first writes, and then when the data on the block becomes invalid, the block can be used again for second writes. Then the user continues to write logical data as he did before, but the physical data on the pages where the data is supposed to go has to be read, because then the encoder produces an output that represents the user's logical data that can be written on the physical target page. Again, this is done until the block is full, and then the block can be erased and used again as before. So notice that since you're using more space than you did, which can be thought of as reserving some space for the second writes when you're performing the first write. Now, this doesn't have to be the 50% overhead that we saw in the table before, but the minimal possible is 29%. That has been proven. So where is this additional storage coming from? Well, you could take it from the over-provisioned space, but that would mean that you can increase write amplification and actually generate more erasures than you would have before. Another thing is that if you're going to use that over-provisioned space for the first and the second writes, you might as well use better error correction codes that need more redundancy and just continue using the SSD longer without all the codes. So the other option would be to take this additional capacity from the one that's exported to the user. But that would mean selling the same device for a smaller capacity, and most of the vendors do not want to do that. Now, other than the capacity overhead, there's also performance overhead, because every I/O operation, read or write, first or second, would have to access between 29 to 50% more bits. And in addition, you have to perform a read before every second write, Other than these two overheads, there's a compatibility problem, because the logical data and the physical data are now no longer in the same size. So you would have to alternate the organization of the flash according to the specific code that you're using. If you don't want to do that, then you're going to have every I/O operation access 2 pages instead of 1, which is even a larger overhead. Finally, there's the problem of applicability. Those codes that have the lower capacity overheads, around 29%, are actually so complex for the encoding and decoding that you cannot really use them in a real system. The latency is too high. So our design of reusable SSD is based on 3 observations. There are 3 things that you do not want to touch when you apply WOM codes to Flash. You do not want to change the interface between the SSD and the operating system. You do not want to harm performance in any way, and you do not want to change the logical capacity that's observable by the user. We're able to do that by using a new family of codes. They're called polar WOM codes. I'm not going to get into the details of how exactly they work, but they're based on the same concepts as current error correction codes. And what's interesting is their characteristics. First of all, they're very efficient. They're efficient as LDPC codes that are used for error correction codes in current SSDs. In addition, they allow you to trade off the amount of overhead between the first and the second write. So for example, we can use a specific code that does not have any overhead for the first write, but has more overhead for the second write. Now, this trade-off comes at another cost, which means that these codes can sometimes fail. What does a failure mean? It means that every once in a while we will have a target physical page and a logical data page that the user is going to write that cannot be written on this page. The WOM encoder will just produce an output that has some ones in the wrong places that cannot be written on the physical page. So our design has to handle those things. We will handle latency by parallelizing, and I'll show you this in a minute. And we'll handle the failures by retrying. These codes have a nice property, which means that you can alter an internal parameter, just an integer, and you can perform a new encoding. Now, the failure of the first and the second encodings are independent. So if you have, and the example that we have in the paper is 5% chance of an encoding failure. For trying twice, the probability of failure is actually as low as 0.25%. Now, even if that fails, we can always go back and take the user's data and just write it as a first write, like it would be written in a normal SSD. Okay, so how is the parallelizing done? First writes are done unmodified. The user writes the logical data, and that's written as is on the flash. So we have the physical pages on the physical blocks until the blocks are full. Once we have a couple of full blocks, whose data has been invalidated, we can recycle them and use them for second writes. Now when the user writes the data, then the WOM encoder produces an output that's twice as larger as the original data. So one logical page has to occupy two physical pages, and they're written on the separate blocks. These blocks reside on different planes, so this can be done in parallel in every current SSD, and this way we avoid the additional latency of the capacity overhead. Now, once we determine that a pair of blocks is going to be used for second writes, we already know which other pair of pages is going to occupy the next write. So we can read the data that's on these pages in advance. That's like prefetching. We bring them into the SSD's RAM. And then the data is there for encoding. So when the user request arrives, then encoding can begin without an additional latency for the read. Again, this is done until the blocks are full, and when this data is invalid, then the blocks are erased, and everything starts over again. Okay, so there is some overhead here because the second writes occupy twice as much space as the first writes. However, notice that the first writes are written as usual. So we can use the over-provisioned space, which usually holds a lot of invalid data, and use it for storing some useful data with second writes. But we don't need to increase the capacity of the SSD, right? We have now more place to store more data. Instead, we allow more blocks to be in this state. So since the data in second writes occupies twice as much space, as long as the number of blocks that are in this state does not exceed the number of over-provisioned blocks, then the capacity exported to the user is exactly the same. So what's the benefit from what we do? Let's look at the standard SSD. To get the number of erasures, you have to divide the number of logical pages that you write by the number of pages in each block. Now, this is best case, no write amplification, just a best case analysis. With reusable SSD, you actually perform 50% more writes. So you divide the number of logical data pages by the number of pages per block plus 50%, and you get 2/3 of the original erasures. That's a reduction of 33% in the number of erasures. Okay, so let's put it all together. To the user, the reusable SSD looks exactly the same as a normal SSD, and everything is done at the FTL level. Now, every plane has the blocks divided into pools. There's a pool of clean blocks that can be used for first writes, and there's a pool of recycled blocks that can be used for second writes. The FTL is in charge of determining which data belongs to a first write and which data belongs to a second write. We use some very basic hot code classification. Again, the details are in the paper. And once the FTL determines that, it can also add wear leveling or load balancing, anything regular FTL does. So if the data belongs to a second write, then it is written in parallel to both of the recycled blocks in the two planes together. If the encoding failed for some reason, or if the data is cold, then we can write it as a first write, either to the first or to the second plane independently. From the perspective of the block, blocks begin their life as clean. They can be used for first writes until they're full and they become used. Once the data is invalid, then the garbage collector may choose this block as a victim. Now, once a block is chosen, two things can happen. If the block is young enough, and actually that's another thing I'm not going into, but we can perform second writes only at the beginning of the block's lifetime. This is around 30%, but we expect it to improve as error correction codes improve. Again, the details are in the paper. But if the block is young enough, and if the number of reused and recycled blocks does not exceed twice the over-provisioned space, we can recycle the block, and then nothing happens. This is just a state change. Otherwise, we can erase the block, just like in a normal SSD, and again, nothing happens that's different from a normal SSD when a block is erased. Okay, if the block is recycled, it can now be used for second writes. So again, until it is full, once the data is invalid, then the block is chosen by the garbage collector, and now the block has to be erased. So there's two things to notice here. First, at any point in time, and this would probably depend on the workload or maybe on various performance constraints that we have, we can abort second writes. The SSD will continue to operate just as a normal SSD, and of course the performance will be exactly the same. But the more we're able to have the blocks cycle through all of these stages, the utilization of the SSD in terms of the number of writes we can perform increases. Okay, so let's put it just in the context of related work and some of the things we've heard of even today. There are many suggestions of how to improve the SSD lifetime. And what's good about reusable SSD and second writes is that they can be used in concert with most of them. So the first two methods, the ones that operate in user level, where the goal is to minimize the number of writes that reach the SSD in the first place, and also similar methods within the FTL that try to minimize the number of writes that reach the flash layer, most of them can be used in concert with second writes, and no special adjustments would have to be made. In the coding level, what usually happens is that error corrections are improved. We have the information theory people trying to work on that. And as error correction codes improve, we will be able to use second writes for a longer period of time within the SSD's lifetime. So this is also good. The final thing is optimizations that are done in the flash layer. And other than the physics things, there were suggestions, for example, for modifying the voltage and the speed of the writes. The exact effect of those things on second writes and vice versa is something that we're still looking into. Okay, so in our evaluation, we wanted to answer several questions. We wanted to know how many erasures are actually saved in practice. We wanted to know how performance is affected, and we wanted to know how sensitive our design is to the various parameters. So we used characteristics from 3 different flash manufacturers. They have different page sizes, read, write, and erase latencies. And we feed them into the DiskSim simulator. We used the SSD extension from Microsoft, and we modified only the FTL component, nothing else. We used trace input from the MSR Cambridge and the Exchange workloads that are available through SNIA, and a couple of synthetic ZIF traces. So let's start with the erasures. The x-axis here are the different traces. The y-axis shows the relative number of erasures compared to a standard SSD. So one would be exactly the same, and lower is better. We have 2 colors of lines here. The red ones are for the enterprise class SSDs. They will have higher over-provisioning values. And the blue ones are for consumer class SSDs that have much lower over-provisioning values. And what we see here is that the reduction in erasures is very close to the expected 33%. Actually, in some of the cases, it's even better. And that's because the simulation ended before all the blocks that were recycled got to be erased, to finally be erased. On the other hand, in some cases, the reduction is less than we expected, and this is because these are traces that have a large amount of cold data that was not directed to second writes. In terms of response time, again, we're looking at the different traces, and the y-axis is the relative average response time compared to a standard SSD. So what we see here is that there's always an improvement in performance, because whenever we save erasures, we improve performance. In the enterprise class setups, the improvement is up to 15%, up to 15% reduction in average response time. And in the consumer class setups, the reduction is a lot larger. And this is because we do not only save the actual erase operation, but we also able to save the entire process of garbage collection. So whenever we perform a recycle instead of an erase, there's some leftover valid blocks that do not have to be copied to another clean block. And in the consumer class setups, where over-provisioning is lower, the number of valid blocks is larger, so the time that we save is actually longer. The graphs and the complete analysis of the rest of these performance characteristics and the sensitivity analysis for the rest of our parameters, everything's in the paper. Okay, so to summarize, this is the first applicable design of performing second writes on SSDs. We're doing it without modifying the logical capacity that's exported to the user. We do not require any hardware modification compared to standard SSDs. And we're doing it with very efficient computation of encoding and decoding. So this is really an applicable design. We're able to perform up to 50% more writes before every erasure, which means we perform less erasures, and this also means that performance improves. Now, performance improves because even though the second writes require more space, we do them in parallel. We're able to prefetch the previous data before the encoding actually happens, and because retries are independent, and because the codes are very efficient to begin with, they do not require us to spend a lot more time than we did before. Now, the good thing is that this is only the beginning, because as codes improve and as hardware implementations and encoders appear for various codes, then we will be able to use more sophisticated codes. We will be able to do it for a longer period within the SSD's lifetime and extend the lifetime even more. Okay, thank you. I'll be happy to take your questions.
Hey, I'm MJ, coming from UT Dallas. That is very nice work. I have just some more questions about the WOM code. So, have you heard about the NOP?
Sorry?
Have you heard about NOP, which is standard for number of program?
The number of programs? I'm sorry.
Yeah, usually the flash memory vendors specify the number of program that you can do on a flash memory. So, if you use the MLC or the triple level cell or multi-level cell, you cannot actually write 2 times on a specific page. Why? Because if you write 2 times, then it's going to make interference issues as well as epipoly coupling issues, this kind of things, which actually corrupt all the data that you're going to do and you're going to write on a specific memories, which is very critical on a WOM code. So I'm curious that how you deal with that kind of NOP violation issues when you do the WOM code.
Okay, so the thing is that indeed Flash is very complicated. So first of all, you have to notice that when we write the second writes, we do it in the same order as the first writes. But again, indeed, there may be some disturbance between the new data that we write and the old data. This is something that we've just started to experiment with and needs some further experimentation. But in the worst case, we can always use just the lower pages, which then should not cause much disturbance.
When you talk about lower page, what it means? Is it, you mean that you just use a SLC page?
But just for the second writes. We don't have to use only the SLC page for all the writes, just for the second ones. But again, this is something that we're not sure we're going to need. It depends on the manufacturer, on the various Flash implementations.
Okay.
Okay, thank you.